Hello, my name is Michal Pulic and I'm gonna show you how to solve the examples number 7. First we start with repeating what we already know. Let's start with geometrical representation of our problem. So we can draw a real affine plane, which is a plane in three-dimensional real affine space. This real affine plane can be seen as an image in three-dimensional space. This image has some bases like b1, b2, and also we can see in this plane some points which are two-dimensional, like the point u, which is approximately 3, 1. Because we would like to represent camera projections to the image, we have to extend this plane to three-dimensional space about shifting everything about beta 3, which can be seen as focal length in our case. Now we have a lines like the blue one which represent the projection rays. Let's draw one more line from point Y to the origin, representing a projection ray for this Y point. Note that X and Y are points in three-dimensional real affine space, so they can be represented as a three-dimensional vector. Set of all lines which are passing through this origin are called real projective plane. These lines in real affine space, or we can say in three-dimensional space, are called points in real projective plane. The points which are going through real affine plane are called affine points, and the points which does not meet this affine plane are called ideal points, or points in the infinite. The affine points in beta, so in the real affine space, can be represented up to scale by three-dimensional vector with coordinates x, y, and 1, where x and y are real numbers. And the ideal points can be represented in beta in this real affine space as x, y, and 0. So this point does not meet the real affine plane. And there is also a condition that x or y does not equal 0. We can define several mathematical operations on this point. For example, cross product or dot product. The cross product does for two vectors a vector which is perpendicular to both of them. So if we write the cross product of xy, we will get a z which is perpendicular to xy. So the dot product actually measures if two vectors are perpendicular or not. If we want to represent something more than just points, for example line, how we can do that? We can start with a representation by the basis vectors like the u and v vectors, but it is not unique. So what could be unique is, for example, the vector which is perpendicular to these 2 points, and it can be obtained by the cross product. So here the z which we wrote is a line incident with the x and y points. The same way we can compute a line for any 2 points, and we can compute for any 2 lines again the point, because if we compute the cross product of these perpendicular vectors, we will get again a vector in the direction of affine or ideal point. So the cross product does line from 2 points or point from two lines. Note that we speak about point for projection ray and line for plane incident with 2 points in real affine plane and one point which is the origin of the coordinate system. Further, I write the relationship between affine and ideal points with respect to homomorphism mapping and the same relationship for lines. So to the example number 1 from our exercises. We should find a representation of x and y. So we extend the real affine plane to the projective plane by adding beta 3, and then write the coordinates just by adding 1 for beta 3. So y will be 3 half 1 1 and x will be 1 half 3 1. The second task, subtask, is to compute a line which intersects these 2 points. So as we explained before, we can do it by cross product. So we will do cross product x cross product y, which is cross product of 1 half 3 1 with 3 half 1 1 vectors, which is 2 1 and minus 4. So our line will be can be represented by a vector 2 1 minus 4 in homogeneous coordinates, so up to scale. In the second example, we have two lines in real affine plane, L and K, which are parallel. We should extend this real affine plane to a projective plane and then find a representation of L and K and their intersection somewhere in the point in affinity, which is called the ideal point. First have to write the coordinates or represent the K and L. One way of doing that is simply find 2 points on L and find 2 points on K, and then create a cross product of L1 L2, these points on L, and cross to generate a line, the coordinates of line, and the same for K. So in our case, L1 is 0 to 1 and L2 is 3 half 0 1. The cross product is then 0 to 1 cross product with 3 half 0 1, and that is 2 3 half and minus 3. For K, we can write K1 as 0 4 1 and K2 as, for example, 3 half to 1, and then the line K would be cross product of K1 K2, which is cross product of 0 4 1 and 3 half to 1, and that's it, 2 3 half and minus 6. So having these two lines, we can again we can compute the intersection of these lines by computing the cross product of two lines. If you can imagine, you will see that we have two vectors which are perpendicular to the planes defined by L1, L2 vectors. And the same we have for K. So if I draw it, you will see that the vector which is perpendicular to K and L is our vector M, which will be a point in infinity, so ideal point. So the way how to compute it is to do just the cross product. We will write it as a vector because everything is up to scale in here, and the cross product of L and K gives us now the coordinates of ideal point which we are looking for. So at the end it is 9, 20, 6, 0. So we can see the 0 at the end, which shows us that it is an ideal point. Ideal. The third task is to find which of following vectors represent an ideal point of the projective plane within standard choice of coordinate system. So we already write the definition how that point should look like. So ideal points should have a 0 as the third coordinate, and they should have at least x or y coordinate non-zero. So if we should represent ideal line, so let's start with an example. We can start with a computation with using the points from the task 3. So if we do a cross product of two ideal points, we will get ideal line. So line in infinity. Each affine plane has one ideal line, and we can see, because everything is up to scale, that if we create a cross product of these 2 points, 1 to 0, cross product 3, 0, 1, you will get 0, 0, minus 6. And in general it is up to scale, so it is 0, 0 and some k, which is some real number. Okay, the task number 5. Here it is, well, a little bit more complicated by the definition of the problem, but generally we have 3 lines in some affine plane, and we have some real projection plane and some mapping to this real projection plane, because there is called image of line, images of everything. So in here we know that the K, L and P are lines which are parallel, and we also know some properties about their images. So for example, the line L prime has a coordinates -1, 0, 3. There are 2 points on K prime line which are, for example, the point K1 with coordinates 0 to 1 and k2 with coordinates 3 4 1. And also we know that on line p prime is a point, let's call it p1 prime, with the coordinates 6 2 2. Our goal is to write a representation of p prime. So first what we should do is to write what is the representation of k prime, the line k prime. So it is the cross product of k1 k2, so cross product of 0 to 1 and 3 4 1, which is minus 2 3 and 6. Then we should compute a point which is common for k prime and l prime, which we will call m. Here I write that it is an ideal point which was true in the real affine plane where k and l was originally. However, we can see that it is not held anymore because k prime and l prime does not have a common point in the infinity, so the third coordinate is not 0. So in the drawing is a mistake. There should not be written ideal point, and k prime, p prime and l prime are probably not parallel in the image, but they were parallel in the original real affine plane. And we can represent m, which is a vector, up to scale. Therefore we can write 3 4 1 instead of 9 12 and 3 coordinates. Now we know 2 points on p prime, therefore we can compute the cross product of m and p1 prime, which gives us the coordinates of a line p prime. It is actually a cross product of 3 4 1 vector with 6 2 2 vector, which is 6 0 and minus 18, which we can write up to scale as a vector 1 0 and minus 3. The sixth task is about computing with homography mapping for lines. So we have a homography which maps p to p prime. We can write it as an equation L prime, where a scaled L prime by a lambda equals homography at minus transpose times a line L. In the first case, subtask, we have a line L in pi, and written that L is an ideal line, therefore L has a coordinate 0 0 and some real number. So if we assign this to the equations which map line to the line prime, we will have lambda times our homography matrix transposed. Now here is a mistake, here should be homography transposed times x, y, z equals our line 0 0 and some real number, let's say k. We write what is the image of L. It is the x, y and z. So x is minus k divided by lambda, y is minus k divided by lambda, and z is k divided by lambda. In the second case, we assume the preimage of is the ideal line, so L prime is ideal line, so L prime will have coordinate 0 0 and some real number. We will assign it to the same equation, so we will have lambda homography matrix transposed. Here is again mistake because the matrix is not transposed, times 0 0 and some real number, which is the representation of L prime, and it will give us the coordinates of its prime image x, y, z. So in this case, x, y, z is the lambda times k for all three variables. In the last 7 example, we have a line P which is represented by 1, 0, 1, and the points which are x and y. X has coordinates 2, 2, 2, and y has coordinates 1, 0, 0. And we are looking for a common point between line L, which is a line which is incident with x and y, and the line P. We will call this point M and compute it as cross product of P and L. However, to compute cross product of P and L, these lines, we have to compute what is the representation of L. So L is the cross product of the points x and y. So the cross product of 2, 2, 2 with 1, 0, 0 vector, and it is 0 to minus 2. Then the cross product of P and L is the cross product of 1, 0, 1 vector with vector 0 to minus 2. So we will get point M has a coordinates minus 2, minus 2, 2, which is up to scale, for example, represented by a vector minus 1, minus 1, 1.